So continuing with the discussion on LDPC convolutional codes, I'll use more of the terminology spatially coupled codes from now on, because the viewpoint we take here is a graphical viewpoint, whereas previously we looked more at the matrix description of the codes. Everything is the same except the viewpoint has changed. So we kind of look at this from a different perspective. Let's say we have, these are little protographs of a block code, say. We talked about protographs yesterday, and this would be a protograph for a rate 1/2 block code. We have 2 variable nodes and 1 check node. And it's one of these multi-edge protographs, and remember, that's no problem because these actually represent a larger ensemble of codes where each of these edges is lifted with a big permutation matrix. So if we had a 3/6 regular block code, we would select a code word, say, to transmit out of this code at this time unit. Then at the next time unit, we'd select another code word to transmit out of the same code. Next time unit, we do the same thing. So we just transmit a sequence of blocks with no connection between the blocks. By the way, the base matrix representation for this protograph is 3-3 because we have 3 connections here and 3 connections here. We had similar things that we looked at yesterday. Now, what is a so-called spatially coupled code? Well, we introduce memory by spreading edges over time. Otherwise, we would take, say, this first protograph, and instead of having all 3 edges from each variable node connect to this check node, we would take a couple of them and spread them to check nodes at neighboring times. In this example, we would take 2 of the connections and spread them to the check node at the next time unit, and we'd take another 2 connections and spread them to the check node at the following time unit. So we're spreading edges in a protograph, thereby connecting different blocks and introducing memory into the system. So we can describe this in matrix term as kind of spreading this 3-3 base matrix into 3 submatrices, B0, B1, and B2. And this introduces a syndrome former memory of 2 because there's the variable nodes at the current time are now connected to 2 adjacent time units by edges. So this corresponds to, if we looked at the H matrix viewpoint, to a syndrome former memory of 2. The constraint on spreading is just that the B sub i's have to add up to the original B that we had. Each B sub I has to have the same size as the original B. By the way, here I'm calling the size of these matrices B sub C by B sub V. They're 1/2s in this case. Remember in the first class we were using C minus B by C. Yeah, so it's the same thing, just different notation. One thing to point out is that you do have, in doing this, you have different choices as to how you do this spreading. This is just one example. And doing the spreading in different ways essentially involves designing the convolutional code in different ways. So you could think of it as choosing different parity check matrices for convolutional code. So now the total transmission, if you connected all these things together like this, you'd get a convolutional protograph of the, again, here we're talking in the protograph domain, but just that's a small graph, but it would be analogous to the type of convolutional protograph we had in the previous class. So it would look like this, and again, we could consider it in general to be bi-infinite. And we have the corresponding bi-infinite convolutional base matrix, which is exactly what we showed in the last class. So this does correspond to the way we looked at it previously. The rate is now, instead of B over C, it's BV minus BC over BV, and the constraint length is again given by the number of variables in each column of this matrix times the memory plus 1. So how do we get ensembles of spatially coupled codes? Again, this is a base matrix. Well, we do that graph lifting operation from the convolutional protograph. So our convolutional protograph would look like this. In our little example, our memory was 2, so we have 3 submatrices across each row. And each of these submatrices was given by 1, 1 in our example, so our rows would look like this. So our B sub C, our number of, there's 1 row in each submatrix, 2 columns in each submatrix, and a memory of 2, or a total span of 3 submatrices in each row. Graph lifting, again using the permutation matrix method of generating a larger ensemble, an ensemble of codes, we would simply replace each one in this convolutional base matrix with a permutation matrix. And all possible choices of permutation matrices would give us an ensemble of LDPC convolutional codes or spatially coupled codes with this constraint length. Okay, B sub V is 2 and MS plus 1 is 3, so we get 6M. So the constraint length depends on the lifting factor. So usually we use big lifting factors if we want powerful codes. So that means we have large constraint lengths. Again, that would be a no-no if we were trying to decode with Viterbi decoding, say, but we're not trying to decode with Viterbi decoding, so it's perfectly fine. So each permutation, if we happen to choose the permutation matrices as circulant matrices, then now if it's a permutation matrix, we would get a circulant would be a shifted identity matrix, still just a single one in each row and each column. Then it would be quasi-cyclic. Again, if we could have base matrices here in which we have integer values greater than 1, just like we talked about yesterday, in which case we would lift that particular entry in the base matrix with the sum of permutation matrices. So if we were adding 2 permutation matrices, we'd have weight 2 in each row in each column of that matrix. You could get different row and column densities just by varying the weights of the entries in the base matrix here, if you wanted to build kind of denser codes. Now, what about now this part of this lecture is a little technical. I'm not gonna, I won't give you an exam on it, okay? I want to say something about distance properties of these convolutional ensembles built from protographs. And the method that we used, as I said, this turns out to be much easier computationally to calculate these distance growth rates than the method that we used when we were doing it earlier on. But in getting to this bound on free distance for these kinds of codes, we go through a couple of steps which relate a little bit to what we're going to talk about later on with thresholds also. So the first issue here is, okay, what about distances? Well, we look at terminating a convolutional base matrix like this. So we started at a particular time, we run it for L, we have L time units, and then we stop it. And this is like a terminated base matrix then. And the fact, this is like, remember when we were talking about, this is in the H matrix parity check domain, but it's similar to the generator domain. We're talking about terminating convolutional encoders. We had to put some input bits into the encoder to drive it back to the all zero state. And when you did that, you actually lost a little bit of rate because those bits that you had to put in were not information bits. They had to be certain bits in order to get you back to the all zero state. And it's a similar thing here. So there's a rate loss associated with this termination process. So the total rate is given by this expression. And if L is large compared to the memory, which it often normally would be, then just reverts to the rate of the unterminated code ensemble. So if we don't terminate, we have this as the true rate. If we terminate, we have a slightly smaller rate. If we use a small L for termination, then we'd get a big rate loss associated with this termination. So for example, a 3/6 regular Same example with this base matrix and the same edge spreading. The matrix, remember, had 6 ones in each row, and it just repeated forever. Now, if we terminated it here very quickly with L equal 4, we'd get a little convolutional protograph like this. The rate here would actually drop all the way to 1/4 if L is equal to 4, because L is just twice the memory in this case. So if you terminated the graph that quickly, you'd get a significant rate loss. One thing to notice again when we can look at it, we looked at it from the matrix point of view, from the graph point of view here again, we notice that these check nodes at the end have lower degrees. The ones in the middle all have degree 6 because this is 3/6 regular. But the termination at both ends causes lower degree checks at the ends, okay? Which is, discuss that more a little later. Now, from a terminated convolutional base matrix like this, it can be lifted using the graph lifting procedure with permutation matrices on each edge. And you can get different lengths and different rates depending on what size lifting factor you get and what size termination length you use. Normally, you would use a large L so that you have little rate loss, and you'd also use a large M. Well, we did see already that the lifting factor M influences the constraint length, and if we want a strong code, we should have a large constraint length. Now, there's another way we can say make a semi-infinite base matrix and make it finite. We can use tail biting. Okay, so with tail biting, it's slightly different termination. I think I mentioned this briefly with regard to convolutional codes, but here I'm just going to mention it briefly again because we're really not talking much about the tail biting, but you can look at it. I like to do it because I like this picture where the dog bites his tail. And you take, in the termination part, you wind up with this kind of portion of the base matrix hanging out down here at the bottom, and the tail biting, you just flip it up and fill it in here on the empty part. Again, remember that this is diagonal, and the upper part and the lower part are all zeros. So you can flip that up here, and when you do that, the rate and the degree distribution are unchanged compared to the bi-infinite matrix. When you flip the lower triangular part up here, that property that you had that these first couple of rows had lower degrees is no longer true. You're back to full, in our example, degree 6 for each of these rows. Okay? So the tail biting version of these LDPC convolutional codes is back to a full 3/6 regular ensemble. If you wanted to look at a tail biting base matrix like this and consider it as and lift it and consider it as an ensemble of codes, it will not perform any differently than the ensemble of 3/6 regular block codes. It is an ensemble of 3/6 regular block codes. It will not have the threshold advantage that you get from the termination procedure where you get the lower degree check nodes at the end. So sometimes people ask with the LDPC convolutional codes, can you make them tail biting so you don't have that rate loss? Well, you can, but you destroy the very property that gives these codes their advantage. Okay. So I always tell people, from my point of view, that it's not interesting to consider tail biting ensembles of LDPC convolutional codes. It has exactly the same properties as ensembles of LDPC block codes. The reason we discuss it here is because it helps us prove our distance bounds. So this again, you can get the rate is exactly the same. You can get a variety of block lengths by varying the lambda, which is the number of columns before you do that you save before you do the tail biting. So you can get various block lengths, tail biting ensembles of various block lengths by just varying the lambda. Now, and there's no details here, but The tail-biting ensembles you can use actually to obtain a lower bound on the convolutional code free distance growth rate. So if we said, all right, here's an ensemble of block codes, protograph, described by a protograph or a base matrix. Let's use the div-Solar approach for getting the weighted numerator associated with this protograph. And let's do the averaging, and let's get the distance growth rate of that ensemble based on that spectral shape function that we talked about yesterday. And you can do that, treat it just like any block code ensemble, like any other block protograph, and you get this minimum distance. These are the distance growth rate, minimum distance growth rate of a tail-biting convolutional ensemble. So the growth rate starts, it's going to start at actually 0.023 because it's a 3/6 ensemble. As you make the tail-biting length longer and longer, you're not making the code any stronger. You're just making it longer. So eventually the distance growth rate starts to fall off and eventually will go to 0. Okay, because you've got a certain constraint length there, and you're just making the length of the code longer without increasing the constraint length. So this can be used to lower bound the free distance of the associated unterminated code. It does go, if any of you have worked at all with convolutional codes, you know that when you don't terminate a code, when you terminate a code, you always get a code word of lower weight. So it always, any kind of termination gives you, or tail biting gives you a lower bound on the weight of an associated code word that would not be shortened by tail biting. So the convolutional, the lower bound on free distance growth rate for convolutional codes looks like this. Now this is the normalization. So why does this go up and this not? The normalization here is with the total block length. I mean, we're treating this like a block code. The normalization here is with the constraint length, because that's the way you normally express the free distance growth rate. It's a ratio of the free distance to the constraint length. And even though the length of the tail-biting ensemble is getting longer, the constraint length isn't changing. So you're not normalizing this by something, you're not dividing by something that's getting bigger like you are here. So that's why this actually increases up to a certain level and then stays constant. Now, if you look at the terminated ensemble, not the tail-biting ensemble, and again, these are all asymptotic results, that the lifting factor goes to infinity. So the terminated ensemble, without the tail biting, can be used in the same way to get an upper bound. So this is the bound, this is the minimum distance of the terminated ensemble, again, using the standard approach that div-Solar uses with weight enumerators of protographs. And then that can be used to upper bound the free distance growth rate of the associated convolutional ensemble, which is not terminated. And that gives this upper bound. And the two bounds meet here if the termination factor is long enough. And this essentially tells us what the free distance growth rate is for these terminated ensembles, as long as we make, these are periodically time varying, as long as the period is large enough, it has to be at least about 12 constraint lengths. So again, I don't expect you to follow this. This is just an idea kind of how we took essentially block code ensembles, two different types, one with termination with a tail and the other with termination without a tail. And we apply the same kind of minimum distance bounding techniques for the minimum distance growth rate of those block code ensembles that we talked about yesterday. Those two results, one gives a lower bound, one gives an upper bound on the free distance of the associated convolutional code ensemble that these block code ensembles were derived from. And these lower bounds and upper bounds meet, at least if you have if the ensembles are periodically time varying with a large enough period. So this gets us back to this picture. okay, which we just, remember I showed it earlier and I said we have the two convolutional code free distance growth rates for 3.6 and 4.8. And the technique, the averaging technique that we used originally, we just numerically couldn't deal with it beyond those. But using this method based on weighted enumerators of protographs, we can get easily any of the growth rates associated with any of the JK regular convolutional ensembles. The X's in this picture are all the corresponding block code ensembles that we showed yesterday. And the circles are the convolutional code ensembles. So we see that the growth rates, like associated with the 3.6 convolutional code ensemble, is larger than the growth rate. It's about 0.086. The growth rate associated with the block code ensemble is about 0.023. But again, these represent different things. One is a free distance growth rate relative to constraint length, and another is a minimum distance growth rate relative to block length. The important thing is these convolutional ensembles have linear distance growth with constraint length. So they're asymptotically good ensembles. So we would expect, and we would expect them, therefore, to have not have problems with error floors. Okay, they perform, even though they have that slight irregularity at the beginning, okay, they still behave like regular ensembles in terms of their distance properties. I also have plotted in here distance growth rates for those ARJA ensembles that we talked about yesterday, those irregular LDPC code ensembles. Those are the solid points here. This is the basic ARJA, and these are the ones that are extended to the higher rates. And we see again that these are asymptotically good ensembles. They have linear distance growth, but they are irregular, so they have much better thresholds, as we saw yesterday, than the regular ensembles. But not better thresholds necessarily than the spatially coupled regular ensembles. So I debated whether to even talk about the termination and the tail biting or just go right to this, but it does relate a little bit to what we talked about yesterday with being able to use the weighted enumerator analysis based on a protograph and then the uniform interleaver analysis for an ensemble based on the protograph to be able to find minimum distance spectral shape functions, which gives us the minimum distance growth rate of ensembles of block codes. And we use that to get the free distance growth rates of associated ensembles of convolutional codes. Okay, now back to the graph-based view here and try to get a little more insight into what is it that gives these things the good thresholds. Again, these variable nodes all have the same degrees. The check nodes have lower degrees at the end. And we can think here, we don't have to. Termination required only at one end. We could consider the other end to be unterminated. But we'll look here in this picture. We'll say we have both ends terminated. Think of the length, total length, as being large. So we have a few check nodes at each end with smaller degrees. And that gives us stronger local codes at the end. And we can visualize the effect of that if we look at the evolution of the erasure probabilities with iterations for a 3.6 regular spatially coupled code with L equal to 100. So here on the horizontal axis is the iteration number, and here this is the time index. Okay, so over here on the left, the nodes, the erasure probability associated with nodes, the variable nodes at the left end of the graph. And over here is the erasure probability associated with the variable nodes at the right end of the graph. And everything in the middle is the erasure probability of the nodes associated in the middle of the graph. Now notice what's happening after 10 iterations. I mean, this is basically nothing has happened in the center of the graph. But the erasure probabilities of the nodes at the beginning and the end of the graph, where we have these smaller check node degrees, which gives us stronger local codes, just the connections that we make between the checks there and the local variable nodes, is starting to improve the erasure probabilities for those nodes. And then as we go to 20 iterations, we see this effect starting to move towards the middle of the graph. Otherwise, more nodes are getting the helpful effect of these stronger nodes, stronger checks at the end of the graph. And this continues if we do 50 iterations or 100 iterations or 200 iterations or 300 iterations. This was a density evolution example that we did for this on the erasure channel for this particular ensemble. So this is an illustration of this wave-like decoding. Otherwise, the low degree check nodes at the end get us started in terms of being able to make reliable estimates on the variable nodes that those checks are connected to. And then those are connected to further variable nodes, and this effect propagates towards the middle of the graph. So eventually we get all the nodes, the erasure probability of all the nodes will converge to 0 if we're operating below threshold. And you know, if you stop with a fixed number of iterations with these spatially coupled codes, you do have unequal error protection. I mean, the bits at the ends of the graph are protected better than the ones in the middle. It takes longer for this wave effect to get to the variables in the middle of the graph. Now, just as a reminder, the fraction of these low degree check nodes, it depends on the number of time units that have low degree check nodes is just the memory. That syndrome former memory, that can be very small compared to the overall constraint length, because the constraint length is essentially the memory times this lifting factor. And the memory typically is small compared to the lifting factor. So the fraction, as we make the graph longer and longer, the fraction of lower degree check nodes actually goes to 0 as L goes to infinity. Okay, so they are irregular, they have a slight irregularity, but we like to refer to them as asymptotically regular or almost regular, or we've used different terms for these codes, because they still, the basic structure is regular. And it's just at the end of the graphs that you have a different structure. So now I'm just going to give some results for, these are numerically calculated results for these thresholds. This was kind of the early work we did on this, on the erasure channel. I think I gave a talk at EPFL in 2003, and I presented some of these results. And Rudy was surprised by the results, as I said earlier, and I said, well, I am too. Okay. But anyway, they turned out to be accurate. So this is a erasure channel. And in plotting here the termination factor L, this is the 3/6 regular ensemble, but with a termination for short L, the rates are lower than 1/2. So this is the Shannon limit for rate 1/2 codes on the erasure channel. This would be the Shannon limit for the corresponding rate given the termination factor. So if we have a very small termination factor, the rates are very low, and the Shannon limit then is much higher than 1/2. Okay, but it comes down and approaches 1/2 as the termination factor gets large. And this curve is the BEC thresholds for this asymptotically regular 3/6 ensemble. And for example, if L is equal to 4, remember that was just with the rate was all the way down to 1/4. The Shannon limit there is 3/4. And the threshold of this ensemble is 0.635. So it's not so close. So it kind of tells you, if you thought, and we have thought at times, well, are these ensembles terminated to a short length? Would they make reasonably good LDPC block codes? And the answer is probably not. I mean, the thresholds aren't that great. Okay. As you go to L equal 10, you get rate up to 2/5, and the threshold is 0.505. That's still almost, the Shannon limit is 0.6, so it's still not that close. But as you keep going, as L goes to infinity, the threshold is 0.488. We've seen this number before, and the Shannon limit is 0.5. Otherwise, this, once it gets below 0.5, after about L equal 20, it just stays constant. And there's essentially no rate loss after that either, because you're so close to a half. And remember that the block code threshold was only 0.429. So these spatially coupled 3/6 regular ensembles get thresholds very close to the Shannon limit, whereas the block codes of the same type lag quite a bit behind in terms of their iterative decoding thresholds. Again, you can make this even closer, as we showed by doing 4.8 or 5.10. So again, the table, this is what we just showed, and this is the block code threshold, but we get almost a capacity even with 5.10. We showed this earlier. These are the same thresholds for the Gaussian channel. And again, pointing this out, that these thresholds are getting better with density, whereas in the block code case they're getting worse. So we get, we can say in some sense we get the best of both worlds, the regular and the irregular. Because we also, with these codes, the spatially coupled, we have the linear distance growth also, unlike many of the irregular block code ensembles, most of the irregular block code ensembles. Now, another way of looking at this in the BEC, you can think of it even a different way. You have these stronger local codes at the end with the lower degree check nodes. And in the BEC, once you've decoded a symbol, you can actually remove it from the graph. And you can shrink the graph, just removing the symbols that are decoded in the connecting edges. So you can think of this wave effect as you decode some symbols at the end reliably, you remove their edges from the graph, and everything kind of shrinks toward the middle until you have everything decoded. Now this saturation, the threshold, I haven't mentioned this before, the number that this threshold saturates to actually turns out to be the map threshold of the underlying regular ensemble. So remember, we showed a couple of those pictures yesterday, and we have a couple here too, where we show the BP threshold and the map threshold. So the threshold for map decoding, or for ML decoding. And there is quite a difference between the two. And the BP decoding of the block codes, you're limited to getting the BP threshold. And if you make the ensembles denser, there's a bigger gap. The map thresholds get better with density, but the BP thresholds get worse. Okay? So again, with the block codes, you'd be stuck with performing with regular block codes. Okay, this is of course the primary interest for irregular block codes. The performance of the BP decoding of the regular block codes as they become more dense becomes even worse because the BP threshold gets worse. But with the spatially coupled version, you wind up actually the BP threshold of the spatially coupled codes goes to the map threshold of the underlying block code. Okay, so, and those map thresholds are getting better with density, so that means that with BP decoding, you can improve the performance by going to larger densities, and you can actually get to the map threshold of the underlying block code ensemble. Now I have to be a little careful here because you may say, okay, well, map decoding is optimum. Does this mean that BP decoding is optimum for spatially coupled codes? No, because that map threshold that you're going to is the map threshold of the block code ensemble. This is a slightly different ensemble. So what I'm sure is true, and actually I don't know if anybody's ever done this. Rudy would know probably, but that the map threshold of spatially coupled is a little bit better than the map threshold of the underlying block code ensemble. So you're getting to the map threshold of the underlying block code ensemble, but that doesn't mean that you couldn't do a little bit better still if you were going to do, if you could do maximum likelihood decoding. Okay, we had a paper where this was demonstrated numerically, and then using a different ensemble. We have always worked with these protograph-based ensembles where we do this graph lifting and everything. To actually prove analytically, you need to give a little more randomness to the ensemble. And this is the approach taken by Urbanki and Richardson and Kudakar in the work that they did initially published in 2011. They proved that the threshold of these spatially coupled codes goes to the map threshold of the underlying ensemble. They proved it analytically. First for the erasure channel, and then a couple of years later they did it for more general memoryless channels. So again, you're getting map threshold, but by slightly modifying the graph of regular low density parity check codes, you're getting map threshold performance with BP decoding, which is linear in complexity, linear in block length, whereas map decoding would be, in general, exponential complexity in block length. I mean, that's really the key. This is the key thing with these spatially coupled codes. I mean, I think they call this a peeling decoder. Once you've decoded bits on the erasure channel, you can peel them away from the graph, so the graph shrinks. For other channels too, if you were sure, if you're confident that certain bits have been decoded, but I don't know whether it would be any advantage because you have to implement the decoder. You can't be, dynamically changing the decoder. I mean, if you do the software, of course you can. But
the actual way the decoding was happening, right? I mean, the decoding was happening more like in a sequential manner, and I mean, the figure you just illustrated that.
Okay, the illustration shows the messages are being passed across the entire graph. Each iteration, you're passing messages across the entire graph. Okay, the illustration was what is the effect on the erasure probabilities. So the fact that the erasure probabilities only at the ends were improving with the initial iterations, that doesn't mean you're just locally updating those. It just means that the updates the stronger information from the lower degree check nodes at the end hadn't had time to propagate yet to affect the erasure probabilities of the nodes in the middle. So that illustration, it does assume essentially that you're doing full flooding schedule updates. All variable nodes and all check nodes are updated at the same time. Now what we'll talk about more this afternoon is when we use a window decoder, which we start, say, on the left side and slide the window across, so that once the initial bits clear the window, then you can decode them. You don't have to wait, so it's much lower latency than this. Actually, decoding this way is actually high latency because you've got a very long graph, and you've got to wait until you get all the symbols before you start decoding. This is more for illustration. So I think in practice, you almost always, unless you've got a fairly short graph, you almost always want to decode with a sliding window. But we'll talk about that more in the next class. Any other questions on this? So whoever was asking me yesterday about standards, I think it was you, about the turbo code standards. And I said, well, they really should be replaced with these kind of codes. Yeah.
Lastly, the iteration previously. This is the maximum convergence probability, or it can still go higher, like 400 iterations or so?
Well, it will, no, I mean, so you still don't have a very good erasure probability here for a few nodes in the middle. So you'd have to keep going here to get everything down. But it's just to illustrate that it does come down. Now, one of the issues is it takes time for the wave to propagate. So that implies kind of a large number of iterations. And that's an issue with now again, practically the way you do this is with this window decoding idea. And we have some results, I'll talk about them this afternoon, but where we do take into account complexity and iterations and things like that. And it's still very competitive. I mean, you don't need, you can have efficient schedules of iterations which are quite reasonable in terms of still getting this kind of performance. But that's all. I mean, these are more like asymptotic thoughts here. And this afternoon, the last class will be more like finite length stuff. Okay, here again, this picture, I think. So we showed this yesterday. Here, this is again, 3/6 ensembles. Here's the BP threshold. Here's the map threshold. This is erasure channel stuff. This is a simulation. And I don't remember the block length, but it's pretty close to the threshold, so it's probably 10,000 or something. And then if we went to 5/10s, for example, we have a much poorer threshold. And so here's a simulation, not very good, way away from capacity here. But we do notice that the map threshold of the 510 is better than the map threshold of the 3/6. So if we can use spatially coupled, we should be able to get here. And these are simulations. This is a spatially coupled 3/6, so we're getting close to the map. This is a spatially coupled 510. And we're getting better, okay, and close to its map. And you can get closer if you use bigger block lengths. Like I said, this is probably 10,000 or something like that. In the spatially coupled case, it would be the constraint length, which is determining the strength of these codes. The lift, basically that lifting factor, M. So we kind of get optimal decoding performance with a suboptimal iterative algorithm. Almost. This is what I said. It's not really the spatially coupled map threshold is probably, oh no, you can't go beyond 0.5. It's not going to be much difference. Yeah. Okay, and this is just the same picture on the Gaussian channel, except here we did it with 4/8 instead of 5/10. And the spatially coupled follow the map thresholds. Again, this is with iterative belief propagation decoding rather than the BP thresholds. Now, these are some pictures. I mean, here this is erasure channel. These are thresholds. This is the Shannon limit. And these three curves are these are thresholds of terminated spatially coupled codes for a given L. For 3/6, 4/8, and 5/10 ensembles. And you kind of see if you have very short termination where you have lower rate, the rate is vertical here, you're not really that close to threshold. You don't really start getting, or you're not that close to capacity here in this case. You don't start getting close to capacity until you get a large L, which gets you up to the nominal rate of a half of these ensembles. And it's the same with the 4/8 and the 5/10. Actually, the 4/8s and the 5/10s are worse than the 3/6 in terms of threshold if you terminate them with short L. It's not until you get, again, the L gets fairly large and the 510 becomes better and actually essentially almost gets the capacity. Now these pictures are the distance growth rates of these ensembles. The JK regular block code ensembles have these distance growth rates. 3, 6, 4, 8, 5, 10. This is the Gilbert-Varshamov bound. These are distance growth rates for the terminated spatially coupled ensembles, starting with the small L, which gives us the low rates, and then as we use larger L, we approach rate 1/2. Now these are, this is the kind of original work we did on this. These are minimum distance growth rates of the block code, terminated block code ensemble. So they're basically when I showed the upper bound on the free distance that you get with the terminated, it's actually this bound, the terminated codes as block codes, minimum distance growth rate, as a function of the termination length L. And that comes down here. It merges with the bound on the minimum distance growth rate of an associated tail biting ensemble, and then it eventually goes to 0 here. Because the code is just getting longer, but the distance isn't getting any greater. So you're basically dividing a constant by something that's getting longer, so larger, so that's going to go to 0. And that's what's reflected in this picture, is the minimum distance growth rates of these spatially coupled ensembles. And the picture illustrates that they do have linear minimum distance growth, so they're asymptotically good ensembles in terms of their minimum distance looked at as block codes. But as the termination length gets long, the actual growth rate is tending towards 0, just from that picture that I showed earlier. So the question is, purpose in presenting these originally was just to show that these had linear minimum distance growth. They have these great thresholds. They're still asymptotically good. But it doesn't make any sense to think that the codes are getting weaker as you increase the termination length L. And the reason is because the strength of a convolutional code really comes from the free distance rather than the minimum distance. So in some sense, these pictures are a little misleading. This is similar results for the Gaussian channel. Now, of course, in terms of distance, doesn't care about the channel. This is the same pictures on the previous. These are just the Gaussian thresholds. And again, we see the 510 ensemble as a worse threshold if you terminate it really short. But when you get up to long terminations, it's going right to the Shannon limit. But this is the point I was making. As L goes to infinity, the minimum distance growth rates of these terminated ensembles tend to 0. Okay? But the free distance growth rates with constraint length remain constant. This was the free distance bound. This was the minimum distance bound for these terminated. This is the free distance bound for the unterminated. This is the minimum distance bound for the terminated. So for large L, the strength of these unterminated ensembles scales with the constraint length. It's independent of L. So the strength of these codes depends on the constraint length, not on L. So a better measure of the strength of these codes in terms of distance, which would affect things like error floors, is not so much this minimum distance growth rate that's going to 0 for large L, but it's this free distance growth rate which is staying at a certain level for large L. So we need to do more work on this, but we're convinced that this is right just because of the results that we see for these codes. If these distance growth rates for large L were really if the codes were as weak as the minimum distance growth rates indicate, we should be showing error floors and be having all kinds of trouble at high SNRs. but we're not, and it's simply because these are convolutional codes, and the strength of a convolutional code depends on its free distance, not the minimum distance over an entire termination length. So that's a little bit of a in the weeds type of comment at this point, but I did want to make it just, if for no other reason, to point out what those graphs were illustrating. Now I'll finish up here with back to our ARJA example for irregular. So as I said, we get what we want with spatially coupled codes with regular by using regular ensembles. But we can use them with irregular ensembles too. And particularly with really nice irregular ensembles like these ARJA ensembles that have linear minimum distance growth and good thresholds, we can make spatially coupled codes out of these too. So this is back to that ARJA example that we finished up yesterday afternoon with. We have to do edge spreading here. Now there's lots of ways to do this. I mean, you can pick whatever memory you want, and for a given memory you can divide up the non-zero entries here however you want. So there'd be lots of different convolutional protographs you could get from this block code protograph. And we made no attempt to try to do this in the best way. We don't know how to do it in the best way. Okay. But this is a way we did it. We used memory 1, and we just split B into these two matrices. This one has this graph associated with it. This one has this graph associated with it. So these would be the two, B0 and B1 that we'd have in our H matrix and our associated convolutional graph. So we get a convolutional protograph that looks something like that based on this irregular ARJA block code. And this is going to have the same rate. It's still rate 1/2, same degree distribution, and same node connectivity as the ARJA graph. Just like when we do this, when we kind of do edge spreading from any other block code base matrix. Now again, the infinite length one here can be terminated, say start at a particular time and end at a particular time. And the resulting terminated protographs can be analyzed using the same techniques. We can do density evolution on these protographs, and we can do weighted enumerator analysis on the protographs. This is what the spatially coupled protograph looks like, or at least the one that we decided we wanted to implement. If we go to the AR4JA, the ones where you had the extra variable nodes to give you higher rates, so those are kind of all included here. They're just it's basically the same graph except extra variable nodes. So you can do these kind of pictures with ARJAs also, and in the distance domain you get again with short L's, you always get positive linear distance or minimum distance growth rates. But again, as your termination length gets large, the minimum distance goes to 0. Minimum distance growth rate goes to 0. But again, the key parameter would be these have free distance growth rates also. We haven't analyzed those, but the convolutional versions would have free distance growth rates. And these are the thresholds, and the thresholds, these are all, this is the basic ARJA is this one. I think this is rate 1/2. And these are the ones with the enhanced, with the extra variable nodes for higher rates. And you'll notice they basically all go to capacity. I mean, these are numerical results, but they're within several significant figures anyway. So these are really good. I mean, doing spatial coupling, they have really good thresholds to begin with, but they're not at capacity. Here's the threshold of the basic ARJA, and it's still a little bit away from capacity. And here's the threshold of the rate 2/3 ARJA, and it's still a little bit away. And this is the rate 3/4, and the rate 4/5. They're still a little bit away. But with the spatially coupled versions of these codes, you can bring their performance essentially to capacity. Again, this is not quite going to be, well, I have to be careful here because I'm not 100% sure, but I say they're not going to be exactly capacity because generally speaking, we need to increase node degrees. We need to increase the density to really actually get to capacity with the map thresholds. These are going to all get to the map thresholds of the underlying ensemble. But these higher rate ARJA codes, they are denser because they're adding all the additional variable nodes. So they are denser. So the fact that they get very close to capacity is not surprising. So they're, again, spatially coupled versions of ARJA codes would be extremely interesting. They will get to capacity a little quicker than the regular versions, but of course they're a little more complex to implement. The structure isn't quite as nice because they don't have the regular structure. I mean, this is just an illustration of like plotting here the fractional gap to capacity for these ARJA codes as we vary the minimum distance growth rate. So we saw as we increase the termination factor, the distance growth rates are decreasing. So we're increasing the rate of the code but decreasing the distance growth rates. And these curves plot the fractional gap to capacity. I mean, we say that this allows a code designer to kind of tune between code rate, distance growth rate, and threshold by varying the termination length and the number of these enhanced variable nodes that you add to the ARJA design. And as you make L sufficiently large, it's just interesting observation that the fractional gap to capacity seems to go inversely to L. So for L equal 20, we're within 5% of capacity. For L equal 50, we're within 2%. And L equal 100 within 1%. I don't think there's anything analytical here. This is just kind of a curiosity of the numerical results that we got. But you can certainly, again, we see just from a different point of view, when we use large termination lengths on spatially coupled versions of these ARJA ensembles, we can get very close to capacity. And this is again another picture like this, which, okay, this one compares, in a way you can compare the regular spatially coupled to the ARJAs here. So let's just take, these are thresholds, this is Gaussian channel, and this is the ARJA ensemble rate of half, and this is the 3/6 regular rate of half. And the 3/6 regular gets to the map threshold of 3/6 regular block codes, which is about 0.046 dB. But the ARJA rate of half gets almost to capacity. And the same thing here. This is the spatially coupled rate 2/3 regular code. And it gets close to capacity. It gets to the map threshold of the rate 2/3 ensemble of LDPC block codes. But the corresponding ARJA with equal 1, gets all the way to capacity. So the ARJAs actually, because they're irregular to start with, they actually have, what it amounts to is they have better map thresholds than the regular LDPC code ensembles. So by spatially coupling the ARJAs, you can get better thresholds than you can get with the regular block code ensembles. Now, on the other side of that, you could get that with the regular ensembles if you go to 4.8 or 5.10. You essentially get to capacity. And it's debatable as to which is easier in terms of implementation complexity. Would you want to implement an ARJA? It's got a lot of degree 4 variable nodes. and an irregular structure, or would you want to implement a 5-10, say, regular ensemble, which is a regular structure but has degree 5 variable nodes? So that's a question for people that deal with implementation complexity. But the performance of these spatially coupled ARJA codes is also really good. So this is just simulations. So spatially coupled codes derived from ARJA irregular block codes. And we're taking the spatially coupled code as a constraint length equal to the block length of the corresponding ARJA code. So this is a little bit hard to see here. This is the rate 1/2. This is the rate 1/2 block code simulation with block length about 2,500. This is the corresponding spatially coupled version of that code. And again, we see about a 1 dB, what we call convolutional gain. Again, this is not, the decoding latency of this would be higher. Okay, but you get a nice gain for that penalty. And these are just the corresponding simulations for the higher rate versions of the ARJA code. And you see in all cases, I won't point to every one, but you still get this convolutional gain with the spatially coupled version all the way up to, I guess the highest rate here is the 4/5. Okay, so you get a nice family of codes with similar design with these ARJA codes, and you can improve the performance essentially to capacity thresholds going almost to capacity with spatially coupled versions. These are really good codes. They were designed roughly 10 years ago at people at JPL, irregular codes with really nice structures and really good properties. And if you look at them as spatially coupled codes, they can do even better. So we use tail biting and terminated versions of spatially coupled ensembles to get to a bound on free distance growth rates for the unterminated spatially coupled ensembles. And we were able to show that they're asymptotically good ensembles, and we get large free distance growth rates relative to what you can do with the general class of codes. I mean, they're short. You don't get all the way to the bound for the general class of convolutional codes, but you can get within a factor of 2 with at least 4/8. So spatially coupled codes display this threshold saturation effect where you get performance of map decoding with suboptimal BP decoding. And they combine, the JK regular spatially coupled codes combine these large distance growth rates with the iterative decoding thresholds, that the threshold saturation effect. And the implementation is still basically based on a regular structure, so it's a simple implementation relative to irregular designs. And for a given graph density, if you design irregular spatially coupled codes, you can also get a well-designed irregular, maybe one that has linear distance growth, can still achieve linear distance growth and even more improved thresholds, but some cost of additional implementation complexity because of the irregular design.
So the sequence is that the BP threshold is on the way of the map threshold of the underlying entity block code. You said that, my question is, how will the map threshold of the underlying entity block code be different from the map threshold of the spatially coupled?
Yeah, okay, that isn't in this statement. Again, the map threshold of the spatially coupled code would be a little larger than this. I mean, this gets you to the map threshold of the underlying block code, which is strictly regular. This slightly irregular ensemble would have a slightly larger map threshold. Again, there's not much, I'm confident in saying slightly larger because there's almost no room left until you get to capacity. So it's not saying that you're going to get optimum performance with BP decoding, even though we kind of are maybe the language is a little sloppy here. We throw the word optimum around, but it's still a suboptimum decoding method, but you're getting the best performance you could get with a closely related blocks code ensemble, but not exactly the same. Any other question here?
You mentioned that spatially coupled code is a more generalized version of looking at the LDPC. Can you give some?
Well, okay. I mean, spatially coupled codes and LDPC convolutional codes are the same thing. The concept of spatial coupling, though, when you look at these graphs, and this is what the Kudakar, Urbanki, Richardson, and a lot of other people now have extended that concept into other areas where this idea of having graphs and linking them together, building memory into the system, gives improved performance. So they've applied this to compressed sensing, they've applied it to multiple access problems, they've applied it to security problems and things like this. So that concept of spatial coupling has gone beyond just saying we're trying to build the best codes, okay? And all I'm talking about here is the coding application. But that's where the representation with the graphical representation really turns out to be useful, because you can see some of these other problems where people have been able to describe the system in terms of a graph like this, a bipartite graph. And if you can describe the system that way, you can do this. You can introduce memory using spatial coupling, and you can usually improve the performance. Yeah. So it's a general concept that has been shown to have a lot of application beyond just the coding area. This is mostly asymptotic stuff. This afternoon I'm going to talk about finite length results, how these compare to block codes with finite length, not just asymptotically.